Hi, here's the first problem from spring 1980. Let A and B be finite abelian groups if their direct sums A direct sum C is isomorphic to B direct sum C. Prove that A is isomorphic to B. So the first way I did the problem, let's zoom out a little bit. The first way I thought to do the problem was to think about, okay, we're in an additive category, so we know that direct sums are going to commute the way that we want, and we can just project onto the factors and construct the isomorphism there. Okay, that was the first solution I had written. That is not the way that the prelim is going to want us to solve it, so do not do that. If your mind goes to that space, if your mind is already thinking categorically and you're already in another structure, that's okay. And it wasn't even that I was trying to do that, it's just literally how my mind thinks, like I abstract and generalize. So that's not what they want. That might get me partial credit, even though it's a completely valid justification and a correct use of what's going on. They're not testing for that. For a graduate algebra course, if you see finite abelian group, I want you to immediately think finite torsion Z module and start working with the linear algebraic structure, and that's it. Just bring it back to the abelian category. Do not go to additive categories. Just keep it in the abelian category. And what do we know about the abelian category, especially with the finitely generated abelian groups, is that we have, since finite abelian groups are finitely generated Z modules, this is a cancellation property for finitely generated torsion Z modules. A direct sum C is isomorphic to B. Direct sum C implies that A is isomorphic to B. This property holds because Z is a PID. Okay, specifically, each finite abelian group decomposes uniquely up to isomorphism as a direct sum of P modules. I call them P modules, but whatever. To alpha I. You can think about this as, they call it the fundamental theorem for finitely generated abelian groups. You can also think of it as the fundamental theorem of arithmetic for finitely generated abelian groups, because it's the same thing. If you think of A as a number, as a composite number, you can always decompose it as a product of powers of primes uniquely, right? That's the fundamental theorem of arithmetic. This is the fundamental theorem of arithmetic for finite groups. And for finite abelian groups, it's pretty much just number theory anyway. So we have that A can be decomposed as these P sub I. I want to make sure I wrote it correctly because this looks like I took P to the I, but that's not it. So that would have gotten me points off, even though I know what I said, but again, we'll just go through it because it looks like I wrote powers, but I didn't mean that. I just got my indices mixed up. The real power is coming obviously from here with this alpha. And so you can, similarly, we can write B and C that way. Now, if they don't, maybe they'll, I mean, this is kind of annoying to write it out because we know what we're saying, right? We can put like an R2 here and then put Z, PI2, Z alpha I2. And you can just do that, or you could even put B if it's like, it's just the indices get so ugly. So they may want you to explicitly write this out, which is, again, especially on a prelim, it's a little bit tedious, and it's also like, okay, just, I don't know, like, let me tell you, if I talked about all my gripes with this test, man. Okay, yeah, alpha C. Okay, so that's like explicitly, when I say similarly, this is what I mean, because the pattern's the same. I'm just changing the variables. All right. So again, now we're explaining exactly what's happening. Hold on. So because direct sums over a PID decompose into primary components, this is exactly what A is saying. This is exactly what it's saying. The isomorphism of A direct sum C and B direct sum C implies for every prime P, so for every P here, A indexed on P, we're just taking it for every P, right? Every P can be mapped this way, piece by piece. So now we just decompose it and we map the powers. A P direct sum CP is isomorphic to B, B P direct sum CP. But classification of finite abelian P groups gives uniqueness of multiset invariant factors. Okay, they're invariant factors, so we could just map them like this. Thus, the components, the invariant factors, are going to be isomorphic, and because it can be decomposed into these invariant factors, we can match them up, and if they have the same invariant factors, it must be that they're isomorphic. Okay, so that's it. All we would have to do is, if we want A and B to be isomorphic, we're looking at, for each P, do the powers match up? And then that's the solution.